So we're going to look at inverse trig functions, and inverse trig functions really aren't, the concept is simply the inverse of a function, which we've covered earlier this year, and now we're specifically going to look at the concept of inverse functions in relationship with these specific trig functions. So the first thing to notice is, for example, if we take our basic f of x equals sine x function, clearly the function is not one-to-one. It fails the horizontal line test for one y value, say 1/2. There are infinitely many x values that I could get for a y value of 1/2. So this function as is does not have an inverse. So like we've done before, we want to look at restricting our domain of this function and letting it be one-to-one, and thus it would have an inverse. So the thing to think about is we have our sine function. The sine function takes on all values from -1 to 1. So we're going to want to restrict the domain of this function where we get all y values from -1 to 1. And clearly there are infinitely many subsections of the sine function where we could get the values from -1 to 1. And what we want to do is simply be convenient about it and restrict our domain so that we're looking at a piece of the sine function from -pi/2 to pi/2. If I look at that piece, we'll zoom in on it here a little, it's this piece right here, be from -pi/2 to +pi/2. And if I look at that piece, I note that if I were to pick a sine value, for example, if I tell you the sine of some angle is 1/3, or the sine of some whoops, hold on, don't want to do that. The sine of some angle is 1/3, or the sine of some angle is, say, -1/5, or the sine of some angle is, say, 0.3241, whatever value between -1 and 1. If I find that value on this piece, the y-coordinate, between -1 and 1, I then can go down and I'll have one and only one x value, angle, that would be the angle whose sine is my number that I give you between -1 and 1. And that's indeed how your calculator works the sine inverse button on your calculator. If you do sine inverse of 1/2, it's going to spit out 30 degrees or pi/6 radians, depending on what measurement you're in. If you hit the sine inverse of -√3/2, then here's -√3/2, it's going to spit out 60 degrees or pi/3. Again, there are infinitely many angles that have a sine of 1/2 or whatever value I pick, but if I restrict my domain to a piece of the sine function which varies from -1 to 1, then I'm going to get, for any sine value, I'll get one and only one angle value in this range from -pi/2 to pi/2. Now we can do the same thing with cosine function. We want to pick, it's clearly not 1 to 1, same deal. We want to restrict our domain and get a piece, a subset of this function that gives us all output values that the cosine takes on, in other words from -1 to 1. And again, there are infinitely many places we could do that. For the sine function, remember, we pick between -pi/2 and pi/2. We can't pick the same thing here because that doesn't give us all possible values of -1 to 1 for the cosine function. So what we're going to do is pick, just again, we could pick a lot of sets, but we're going to pick something around the origin. We're going to pick from 0 to pi, because from 0 to pi we get all y values between -1 to 1. So if we restrict the domain of the cosine function from 0 to pi, I'm getting all values from -1 to 1. So that function right here, a subset, if you will, of the cosine function, that function with a restricted domain will have an inverse. It's 1 to 1. And we can do the same thing with the tangent graph. Our tangent graph has asymptotes at -3 pi/2, -pi/2, pi/2, 3 pi/2. and it consists of these snakes that rise from left to right. The function as is clearly does not have an inverse, does not pass the horizontal line test. The range of the tangent function is negative infinity to positive infinity, so I want to pick a slice that's going to give me all possible output values, and I could pick any one, but again, we're going to pick something close to the origin, close to the point 0, 0, and we will pick from negative pi over 2 to pi over 2. So my tangent function with a restricted domain from negative pi over 2 to positive pi over 2 exclusive, note those are asymptotes, so I do not include negative pi over 2 to pi over 2. But if I look at that function now, it passes the horizontal line test. It's 1 to 1. If I give you a tangent of some number, tangent of an angle is say 7.2, I find 7.2 on the y-axis, slide down, I'll get one and only one angle in this restricted domain tangent function that will have a sine of 7.1. Sine of, or tangent of 7.1. Suppose I have the tangent of some angle is negative 3.2. Find negative 3.2, and then find the angle, one and only one angle for this subsection of the tangent function will have a tangent of, say, negative 3.2. So in summary, and the way our text is going to present this is we are going to talk about the capital sine, capital S sine function, capital C cosine function, capital T tangent function, and those are going to be subsets, restricted domain subsets of our general sine, cosine, and tangent graphs, and specifically they give us, we want them to give us all possible output values, negative 1 to 1. For the sine function, our domain included negative pi over 2 and positive pi over 2 because that's where our sine was negative 1 or 1. Our cosine function, we went from 0 to pi, so we had all y outputs for the cosine function from 1 to negative 1. And the tangent function, remember, has asymptotes at negative pi over 2 and pi over 2. Those are not included in my domain here. And I run from negative pi over 2 to pi over 2 exclusive. And again, our textbook, and it's not particularly commonplace among other textbooks, but they're really going to emphasize this split domain, this subset of the general sine, cosine, and tangent function by actually giving it a capital letter and calling it the invertible sine function, invertible cosine function, invertible tan function, and invertible meaning a function that has an inverse. So we have these functions, these three basic trig functions, sine, cosine, and tangent, that we've looked at, restricting their domains so they will be invertible. And obviously then the question is, what does the inverse look like? Another question would be, do other functions, the secant, cosecant, and cotangent function, have inverses? And the answer is yes, they do. We would also have to restrict our domains in a likewise way to make them 1 to 1 to be invertible. We'll look at those a little bit, but primarily we're going to focus our attention on the inverse sine, cosine, and tangent functions. So for example, if we look at the cosine function, and we'll look at just one here, if I look at the capital C cosine function, we said that's going to go from 0 to pi, and that gives us all of the outputs from negative 1 to 1. We know that the inverse, well again this is y equals capital C cosine x, the inverse cosine function will be y equals cosine inverse of x, and sometimes other notation of this will be arc cosine of x. This arc sine, arc tan, arc cosine notation will also be used in various textbooks or contexts, so you should just recognize arc cosine is the same alternative notation for cosine inverse. So then we know we're done basically in terms of new concepts, because we know how to graph inverse functions, x's and y's reverse. So instead of going from 0 to pi on the x-axis, x and y's reverse, I'm going to go from negative 1 to 1. and all my coordinates are going to reverse. So this is 0, 1, so I'm going to have 1, 0. If I go and look at the graph of this, it is going to look something like this. And where I had up here pi over 2, 0, I'll have 0 pi over 2. Where I had again 0, 1, I will have 1, 0. Where I had pi negative 1, I'll have negative 1 pi. So we know what the graph of the inverse looks like. And we can do the same with sine inverse or tan inverse. And I'll let you check out the textbook and or do that on your own. So some examples of questions or workings, thinkings with these sine inverse, cosine inverse, tan inverse functions. Suppose you're asked to evaluate sine inverse of root 2 over 2 or any of these other things here. It kind of works like Jeopardy. Remember, with the inverse function, we switch the x and y. So now my input for a sine inverse function, this input is a trig ratio, and I'm looking for the angle that has that sign. And furthermore, the sine inverse, remember, we're looking between negative pi over 2 and positive pi over 2. So what angle between negative pi over 2 and positive pi over 2 has a sine of root 2 over 2? And the answer is pi over 4. Next, cosine inverse of negative root 2 over 2. We remember that we pick our angle between 0 and pi, and we're looking for an angle between 0 and pi that has a cosine of negative root 2 over 2. And that's going to be 3 pi over 4. Tan inverse of negative 1. We remember that we're going to we're looking for an angle whose tangent is negative 1 between negative pi over 2 and positive pi over 2. And that answer would be negative pi over 4. Sine inverse of 1/2 over here. Sine inverse again, we are going to restrict our search for the angle between negative pi over 2 and positive pi over 2. So my answer is pi over 6. Cosine inverse of negative 1. I'm looking for an angle between 0 and pi that has a cosine of 1. That will be 0. And I'm looking for tan inverse of 0. I'm looking for an angle between negative pi over 2 and positive pi over 2 that has a tangent of 0, and that will be 0 as well. The tangent of 0 is 0. Just going backwards here, the tangent of 0 is 0. The cosine of 0 is 1. The sine of pi over 6 is 1/2. The tangent of negative pi over 4 is negative 1. The cosine of 3 pi over 4 is negative root 2 over 2. The sine of pi over 4 is root 2 over 2. So just a couple other examples of types of evaluation problems. A little more difficult because we got composition of functions, and we've got to think these through carefully, particularly types of the second one involving cosine inverse stuff. But here we go. Let's suppose I'm asked to evaluate the sine inverse of the sine of pi over 6. We remember the sine of pi over 6 is going to be a trig ratio. The sine inverse of a trig ratio is an angle. I note that from our work before, if we have a composition of inverse functions, we should get what we started with out as an answer, pi over 6. And let's think about that for a minute. If I take the sine of some angle, I get a trig ratio. I'm then looking for an angle that has that as a sine. Well, guess what? It's what I started with. So that's one way to think this problem through. The other way, which will also be useful when we look at the second example, is to actually do it out. I can find the sine of pi over 6. The sine of pi over 6 is 1/2. So then I'm looking at the sine inverse of 1/2. We remember that we pick sine inverse. We're looking for an angle between negative pi over 2 and positive pi over 2 that has a sine of 1/2. And our answer is pi over 6. So the second example down here, it looks very similar. We have our composition of two inverse functions, and it looks like our answer should be indeed just 5 pi over 4. But if I think about that for a minute, Cosine inverse, I'm looking to pick an angle between 0 and pi, and 5 pi over 4 is not between 0 and pi. So the answer can't possibly be 5 pi over 4, because for cosine inverse I pick from 0 to pi. So if I do this one out, I have to actually think it through. Cosine of 5 pi over 4 is negative root 2 over 2. 5 pi over 4, third quadrant angle, cosine is negative, reference angle is 45 pi over 4, negative root 2 over 2. So now I'm looking for the cosine inverse of negative root 2 over 2. I'm looking for an angle between 0 and pi whose cosine is negative root 2 over 2, and that answer would be 3 pi over 4. So, again, these are some of the types of problems that are going to come up in this section, and we'll do another video as well on section 7.6 for you. Ciao.